then maybe they understand it better. But as an information theorist, I did not understand what they were trying to say using this language. Uh-huh. So I use, so apparently, so this result is true. So e to the minus phi x transpose ax integral is determinant of a to the negative half. So 1 over square root determinant of a. So that's why, yeah. Okay. Okay. Sorry? Because of the Gaussianity, yeah. So x transpose ax is like the Gaussian, and Gaussian density integrates out to 1. So basically, it's the 1 over 2 pi to the n determinant of k kind of factor there. Yeah. They are any linear as long as they are surjective. So which means that the row rank should be the full row rank. Yeah. It has to be onto. Yes. Okay. Okay, so I'm going to tell you the interpretation that was discovered in this particular paper by Carlin and Cordero-Ruskin. That made a lot more sense to me. Okay, so here's the theorem that they have. So the theorem is, all right, so they say that suppose an inequality of this form holds. So suppose you have this inequality for some collection of Bj and Pj. If this inequality holds, which is integral of product of fj bj x to the pj less equal some c times or rather this inequality holds if and only if another inequality holds, which is okay. So has anyone not seen the entropy function? I'll just quickly define it in case. So h here is the entropy function. So it's if you're given a density, if you're given a random variable which is distributed as some density f, then the entropy of f is given by this integral minus f of x log fx dx. Okay. When the integral exists. So this result is saying that on the top you have this functional inequality, which says that some this inequality holds for all possible functions. On the bottom you have an entropic inequality or an information theory inequality, which says that take any random variable x. So take x. So x is Rn valued. It's an Rn valued random variable. This is essentially like a sub-additivity result of entropy, saying h of x is less than some constant, some correction factor, plus the entropy of x when you sort of project it in the appropriate dimensions. Okay. So for example, you might be familiar with the standard subadditivity result, which says that let x be x1, x2, xn, then h of x, which is h of x1, x2, xn, is upper bounded by sum of h of xi. Okay. So entropy of x is upper bounded by entropy of the sum of the entropies of the individual components. So you can think of this result as basically being the same as this result, where your bj's are the projections onto the coordinate dimension. So x1, this is just bj is projecting onto the ej vector, and these pj's are all 1 and c is also 1. So that happens to be, so that is basically the same as that. What this general subadditivity result is saying is that this subadditivity relation does not just hold for coordinate projections, it also holds for projections into arbitrary subspaces, but there is going to be a correction factor, which is this log c. And it's not just that this inequality holds if and only if this inequality holds, there's also like an exact correlation between the maximizers. Okay. So on the top I said that it is enough to consider only Gaussian functions fj to find the value of c. The information theoretic counterpart is that if you're trying to solve this optimization problem, where you're trying to find C, so you want to find what is the supremum of h of x minus sum of pj h of bjx. In which expression? Oh, in H. So x is a random variable in Rn, and its density is f. Yeah. So yeah, maybe I'll say f sub x to distinguish it from the f's that I've used before. So it's just the density of f. So given any random variable, you can calculate its entropy by integrating f log f and putting a minus sign. No, yeah, this f is not the same as the fj's that I've used before. So maybe. So the result is for all f, for all density. Yes. So for all random variables x, you calculate h of x and minus sum of pj h of bjx, and this is the same as calculating the supremum over, let's say, g, where g is Gaussian. So g is Gaussian of h of g minus sum of pj h of bjz g. Okay. Right. So that's the connection between the functional form and the entropic form, and I find the entropic form much easier to understand. So what's happening is basically I relate it to this particular form. So I understand subadditivity of entropy in this notation. And what this result is saying is that it's giving me a subadditivity result where now instead of projecting along EIs, I can project along arbitrary subspaces. And there is a correction term. And it just so happens that to find the optimal correction term, you can plug in Gaussians. So that part is still somewhat mysterious why you need to plug in Gaussians. But maybe because I've seen things like this before, when I see entropic stuff and Gaussians showing up, everything makes sense. Okay, so that's what I'll say for that. And so my plan is now to explain this particular. So that's the only proof that I'll go very much into detail. How does this functional form imply the entropic form, and how does the entropic form imply the functional form? Okay, so that's the proof that I'll do in some detail. Yeah. So this is the Braskamp-Leib inequality, that this inequality on the top holds. So it was proved by Leib, but I think Braskamp also had so not the most general version, but some version of it. So it's called the Braskamp-Leib inequality. Yeah.
What was the condition? What are the assumptions to get equality? Even the maximizer is Gaussian.
That's right. Yeah. So right now there are no assumptions. All we are saying is that C is the maximum value of C is obtained when everything is Gaussian, but I haven't said when that is finite. Yeah. So it could be infinite. So there are some questions that haven't been answered. So when is C finite? C finite. So this will require some conditions on the BIs and the PIs. Some condition. The second question is the optimal value of C attained? So it could be, since this is defined in terms of a supremum, it could be that it's never attained, but you're sort of tending to it. So one would be, another question is extremizers or optimizers, do they exist? And the third question would be, if they exist, are they unique in some sense? Like, are they only Gaussian extremizers? Or because the theorem is not saying that Gaussians are the only optimizer. It's saying it's enough to look at Gaussians, but maybe there are non-Gaussians who also give the same value C. Okay, so the third is there extremizers unique in some sense? And just to these points are not, or the uniqueness of extremizers is not obvious. So it's not just a question of let's prove that Gaussians are the only extremizers of this inequality. Because, for example, this is also a Braskamp-Leib inequality, but here you get equality whenever x1, x2, xn are independent. So it's not just for Gaussians. Of course, you get equality if you also have a spherically symmetric Gaussian, but you also get equality for other examples. So that's why these two really do depend on BIs and PIs. Yes.
That optimization there, because for the entropy minus whatever, that would take the entropy maximization is some Lagrangian equalizer,
Uh-huh.
right? So
Yes.
those features are Lagrangian. Is there an interpretation of that for?
I don't know of any such interpretation. Yeah. I guess PGs are fixed, so
Yeah, I mean,
for a particular, yeah.
I mean, it looks like you are trying to maximize the entropy of X such that the entropy of the projection is at least something.
Right, right, yes.
When penalized, it would look like something.
Yeah. Yeah, that's what you're thinking of. Yeah. Okay. So I'll go through the proof of showing why these two are equivalent, and then we'll take a break. Sorry? Oh yes.
What's the relation between the random variable X and the complex F?
Yeah, it's not obvious. It needs to. It comes up in the proof, but it's not immediately like X has distribution or X1 has distribution F1 or proportional to F1. There's some relation, but it's not direct between the F. Yes. Yeah. So Shearer's lemma can also be thought in an entropic. It also has an entropy. So for example, Loomis-Whitney is. So there is another inequality in information theory called Hunks inequality. It says something like if you look at h of x1, x2, xn, then this is less equal. So h of x1 dot dot dot, and you skip xi, and I equals 1 to n, and there is a term of 1 over n minus 1, I think. So this inequality is the analog of this inequality is the Loomis-Whitney. So this is an entropic inequality. So you could basically ask the question. This theorem is saying that every functional inequality has an entropic counterpart. So what is the entropic counterpart of the Loomis-Whitney inequality, and this inequality will show up. Yes. All of them belong to this class, yeah. Okay. Right, so both those inequalities are there. So I'll first do maybe there's a very quick lemma before I do this, which establishes the connection. The lemma is just that the lemma is essentially the proof of the lemma as well. So let's say you have this f log e to the phi over f. So f is some function from a positive function r into r, phi is some function from r into r, and you're calculating this integral. So this integral is, you can use Jensen's inequality and see that, so this is an average of logarithms, so it's going to be smaller than log of the integral of e to the phi. So this is by Jensen. But this left hand side is also equal to integral f phi plus h of f. So log of e to the phi is phi, so that gives me the f phi, and log of 1 over f is minus log f, so that gives me h of f. So I have this inequality. So integral of f phi plus h of f is less equal log of integral e to the phi. Okay, so this inequality is always true. Just Jensen's inequality applied to some two functions f and phi. And in particular, so you can now throw this f phi on that side and say h of f is less than equal to log of integral of e to the phi minus integral of f phi for every function phi that you can think of. Okay, so f with some density, say, just take any phi that you like. The right hand side is going to give you an upper bound on its entropy. Okay, so in particular, not only is this less equal to h of f is equal to the infimum of this over all phi. Okay, and that's because if you were to choose the right possible phi here, you would actually get equality here, right? So you have equality in Jensen's inequality if e to the phi over f is a constant. So if you were to choose your function phi correctly, then you have equality, in which case this infimum is achieved by that phi. So that's the lemma that we have. So this is like a variational characterization of entropy. Entropy is just the minimum of this over all possible functions phi. Yes, yeah. Okay. All right, so now so let's prove the entropic form first. Proving the entropic form. So if you want to prove the entropic form, we assume the functional form holds, and then we want to prove. So so let f be any density on Rn. Yeah. We didn't assume. So we use concavity of logarithm. Yeah, and the fact that f is a density, it integrates out to 1. Yeah. Yeah. Okay. So let f be any density on Rn, and for now let's just pick some functions phi1, phi2, phi_m. Pick some functions phi1, phi2 dot phi_m on the appropriate dimension. So phi1 is some function on R to the n1. This is on R to the n2, R to the nm, and define this function phi from Rn to R. Sorry? Yeah, R plus. So everything is R plus every time. Yeah. As Pj and phi j of bjx. Okay. So we haven't yet explained what these functions are. I'm just saying, just for now, just pick some functions that you like. Later we'll optimize on these choice of functions. So pick some phi1, phi2, phi_m and define this new function phi on the original space Rn as some weighted sum of these functions. So take your x, project it into the correct subspace using bj, apply phi j and add them up. Yes, they are the domains. Yes. So this is defined on this space to R, so to R plus. Yeah. Yeah, Rn to R plus. Yeah, the range is R plus, the domain is R. Okay. Okay. So now, so we have this. So we have this this original lemma that we had, that h of f is given by or is always less equal log of integral of e to the phi minus integral of f phi. And the phi function that we are going to plug in is this phi function that we just defined. Okay, so this is equal to log of integral of e to the sum of pj phi j of pjx and dx minus integral of, so f phi. So if you look at f phi, this is so think of it as a random variable. So what you're basically doing is you're taking the expectation of a random variable over so expectation of a summation is sum of expectations. So you can essentially write this term as fj phi j, where fj is the density of bjx. bjx if x is distributed as f. Okay, so there's nothing really fancy going on. We are just saying there is a sum going on here, and you're integrating over the original space of x over Rn. Might as well integrate over bjx, where the bjx is now your new integral, and this is sum of j going from 1 to n, and that's that pj sitting here. Okay, so nothing fancy so far. We just wrote this, and now we can use Braskamp-Leave inequality. So if you look here, this is e to the summation. So e to the summation is product of e to the somethings. Braskamp says that integral of product is less than product of integrals. So you should be able to now replace this by using Braskamp as log of product of these integrals. So integral of e to the phi j whole to the power of pj, and minus this sum of pj fj phi j. Okay. Okay, so now log of a product, again you can simplify this and write this is essentially just a sum. Oh, so I forgot the c. So there is also c because Braskamp also has that constant c times product. So I'm going to get a log c, log of c plus, so log of a product is sum of pj times log of e to the phi j, integral of that, minus fj phi j. Okay, so I just pulled out the pj and wrote this. And now I'm going to again look at that inequality that we had. So h of f is infimum over phi of something. We haven't yet picked phi. This inequality is true for all phi. So let's now pick the best possible phi that will give us an equality here. So when it gives us an equality, what do you get? You get h of fj, which is the entropy of bj of x. So what you end up getting here is log of c plus sum of basically entropy of bjx times pj, and j equals 1 to n. Okay, so this log of integral e to the phi j minus fj phi j, I'm going to plug in the best possible phi. If I plug in the best possible phi, I'm going to get entropy of this fj. Now, I'm going to get h of fj. H of fj is basically h of bjx because fj is the density of bjx. So I could as well write this as h of fj, h of fj, and h of fj is the entropy of the random variable bj times x. So that's the inequality that we want. Okay. So
you have done that for every feature.
Yeah, you don't. Yeah, you can use actually any function. Yeah.
But the only reason you can do that because you say that your domain on your function over Rn over one.
Yes. Yeah. So as long as it's an onto function, I mean I haven't used anywhere that this bj of x is a linear map from Rn to Rnj. You can, as long as it doesn't even have to be R. Actually, it can be some space Euclidean space H and some other Euclidean space H and some map between them. Yeah. Yes. No, they are not the. So this. Yeah. So this fj is the density of the random variable bjx. It is, and that fj was just some function. It doesn't have to be density. Yeah. Yeah. Yes. Mm-hmm. Right. Yes. E to the phi is equal to the marginal, bj of x. Yeah. Phi, yeah. Yes. Yeah. That's right. Yeah. So, but to prove the reverse, we start out with a phi which is making the first inequality tight, and use an inequality at the last. Yes. So this not. So you mean for h of f to be exactly equal to? Not entirely sure because that the extremizers, because we are also using the fact we are using the Braskamp inequality here. Yeah, so we already need some extremizers to exist to prove that extremizers exist. So Yes. Yeah. Yeah. So. Yeah. Okay. So we are not really proving the inequality. So if this were a proof of an inequality saying h of f is less than this, then yes, then you need equality in all these steps to make sure that extremizers to basically find the properties of the extremizers. But we are doing something funny here. We are not proving the inequality. We are saying if the other inequality holds, then this inequality holds. So in order for there to be equality here, there first needs to be equality in that other inequality, which is the functional form. So then, so that can be used to relate the extremizers in the functional form to the extremizers here, but you can't prove the existence of extremizers. Yeah. Okay, so we could take a 5-minute break here. So I'll maybe skip the opposite half of this. So this is saying that the functional form implies the entropic form. The reverse form is saying start with the entropic form and prove the functional form. It's the same kind of an idea. So the only thing we need is this variational characterization, and then it follows. Okay, so I'll take a break here. What's the dual? Oh. No, I don't use it anyway. Yeah. So Fj is the density of Bjx. Yes. Yes. The lower one or the upper one? Oh, this. Oh, the one at the right at the top. Oh, just below that. Okay. Yes. Yeah. Yes. So Bjx. The notation is that entropy of x. You call it h of f as well. Yes. Exactly. Yes. Yeah. So entropy of a random variable is defined in terms of its density. So when you are talking about h of bj of x, that is an integral of its density, fj log fj. It's the same thing. It's just a notation. So entropy of x is the same as entropy of its density. So h of fj is the same as h of x. It's just that bj of x has density fj. So this h of fj is h of bj of x. It's the same thing, just different ways of saying this entropy of the same object.